Welcome. I'm Paul Morin with the Energy Conservatory, and welcome to our webinar, TEC Training Tools. In this webinar, we'll be covering 6 of our training tools: the blower door simulator, the ZPD simulator or zone pressure diagnostic simulator, our DG700 simulator, our ZPD CU zone pressure diagnostics calculation utility, CStack, and we'll also do a brief overview of our TEC, our TEC trainer, which is a device where you can set up and do a blower door test or a duct blaster test in front of a classroom. A few housekeeping items first. If you're not hearing anything on your system's computer, you'll need to dial in and listen to the presentation over the phone, and on the right side under audio, you'll find a number where you can dial that number in. If you have a question for the presenter, please type it in the question box at the right of your screen. We will be answering questions as we go through the webinar. If I respond to a question, then everybody will see that question. Any questions we don't get to during the presentation, you'll receive an email response within a couple of days. In our webinar will be available on the Energy Conservatory website and also on our YouTube site within a week or so. In this section, we'll be demonstrating the blower door simulator, and this allows you to do a virtual blower door test that includes some baseline readings that include stack effect and the wind effect of the building. And it will also introduce a way to determine the accuracy of your test on a windy day and making density corrections, so you'll be getting more accurate blower door readings. As you can see on the upper left here, it shows what type of test you're doing. We're running a depressurization test from inside the structure, which is the most common way people are doing blower door testing. It allows you, it has buttons for connecting tubing and buttons for choosing the ring you're using on the fan, and then there's a slide bar for controlling the speed of the blower door fan. Now I'm going to go up to setup, so it'll set up our conditions for our test. And so the second pull down menu up here is labeled setup, and I'll click on that and choose set conditions. And this allows you to set up your test options. So you can locate the gauge inside or outside the building. You can do a depressurization or pressurization test, choose your fan type, building style. Will affect the your baseline readings. So 1-story, 2-story, 3-story warehouse. I'm going to choose 2-story for our test. Warehouse simulates about a 4-story building. You can enter your CFM 50, your actual CFM 50 of the house, indoor and outdoor temperatures, which will affect the stack effect of the house. I'm going to enter 20 degrees in here because we are in Minneapolis. I'm gonna just leave 0 for elevation, and the temperatures and elevation will affect the density of the air, and we'll go over density corrections because your gauge won't take that into consideration. And then the wind conditions, and we'll choose a light wind condition, so we'll have some wind variation in our baseline numbers also. Then we'll go over the tubing connections. So we'll click on connect tube number 1, and channel A is reading house to outside, and we're inside the house, so we'll connect a tube going to the outside. So house, we don't need a tube on the input because we're in the house, and we'll run a tube to the outside, house to outside. And then tubing number 2 reads the fan pressure, and let me put ring B on, so we'll show the flow sensor. So the flow sensor is this white donut shaped device that's attached to the inlet side of the motor, and there's a tube running up to that, to the tap on that you connect your tubing to. And so we're reading the pressure at the flow sensor of the fan, and based on which device and ring configuration we have, it converts that pressure to a flow. So channel B is reading fan pressure with reference to the space that the flow sensor is in, and we can see the flow sensor, it's inside, so we don't need to connect a tube on there. And then I'm going to go up to the options menu and we'll analyze that setup, and it says test setup is correct. So let's say we had connected tube number 1 wrong, and we go to analyze setup, and it will say channel A tubing configuration is not correct for a depressurization test conducted from inside the structure. So it reminds you your test setup and that the tubing was not connected properly. So connect that back up properly. Okay, then we'll click remove all tubes, and we'll go on to the second setup, and this we'll do the gauge location outside. So now you can see it flip the fan around. So now we're standing outside with our gauge. So you may do this if maybe you're testing a duplex and you've got 2 fans set up outside the building, and you're controlling both fans with one person. It would be helpful to have your gauges outside in that type of test. Or maybe you're testing individual apartment units. Instead of a blower door fan, you're using a duct blaster fan that's easier to carry around, and you're set up in the hallway, and you're plugged in with a long extension cord in the hallway, and you run your blower door test, and you loosen the cam levers, grab the whole fan and frame, and walk down the hall and put it in the next door. So that can greatly speed up your test. So there are applications where you'll want to do a test where you're standing outside the structure and have the gauge outside the structure. So the tubing connections for that, remember again, channel A is house with respect to outside. We're outside, so you don't need a tube on the reference. So we'll connect our tube and run it to the inside. So house with respect to outside. And channel B, the input is the fan pressure with reference to the space it's in, and the space it's in is in the house, so we need to run another tube to the house. We could also use a T connector, your gauge. If you've wondered what that T connection with 2 little short pieces of tubing on is, this is one of the applications where you can use that. You can connect the 2 short tubes, one to the reference and one to the input, and then run a single tube to inside the structure. So these 2 channels are across from kitty corner from each other are reading the same pressure, so you only need 1 tube, and you would connect one of those tubes to that T in the connection. Alright, and we'll go up to analyze our setup, and it says the test setup is correct. So remove the tubes, go up to setup again, we'll change our test conditions, and we'll do a pressurization test from the outside. And a pressurization test you would typically do if if maybe you have asbestos vermiculite in an attic, or maybe you know that there's mold in the walls and you don't want to be drawing air through the walls. There may be reasons where you'll be pressurizing a house. So we're standing outside. So again, we are outside, so we don't need a tube outside. We need to run the tube to the house. So now we're housed outside. Channel B is the fan pressure with respect to the space it's in, and we can see the flow sensor. We don't need a tube connected to there. And we'll go up to options and analyze our setup, test setup is correct. Remove all tubes, setup, set conditions, and now we'll do a depressurization test from outside. So now the inlet side of the fan is inside the house, it's blowing air to the outside, depressurizing the house, and we're standing outside with the gauge. First tube, again, we'll go house to outside, and our fan pressure with reference to the space it's in, we can't see it, it's on the other side of the panel, so we'll connect our third tube that way. Options, analyze setup, our test setup is correct. Okay, let's go back to our default position, which will be running most commonly a depressurization test from the inside. And let's so we've already set up our test conditions, so we'll connect house to outside, fan pressure. Now let's cap our fan, we'll add the no flow plate, and we'll do our setup for our blower door test. So first we'll click the on off button to turn it on. We'll notice that when we first turn that on, let me turn it off and on again. You may or may not have noticed that on channel B, when you first start up, you get a number here, and that's the voltage of the battery. And with new batteries, you're usually just over 9 volts, and when it gets down below 6 volts, it'll start giving you a warning that your battery is low. So every time you turn on your DG700, it kind of gives you a warning on how close you are to needing to change batteries. So we can see our baseline is fluctuating a little bit because we've got a slight wind. We will click mode, and we'll change our mode to pressure flow at 50. Our device is blower door 3, which is what we want. We're going to leave it at open fan because we know we're at about 4,000 CFM. And now we're ready to enter the baseline reading into the gauge. So we'll click baseline. Baseline will flash. We'll click start. Now it's going to start our time averaging. So it's averaging over time. And as this number stabilizes, we'll click on enter. So enter our baseline reading. Now it's displaying an adjusted baseline reading. So now we're going to be inducing a pressure of 50 on the house. We're going to be changing the pressure in the house by 50 rather than just going up to 50 pascals. All right, so we're ready to start running our test. So we'll click on open fan, which will take all the rings off. We'll hit begin cruise and start fan. So now we're going to ramp our blower door up to 50 pascals, so we can see on the lower left here that our fan is turning, our fan is running, our slide bar is moving, and adjusting the fan speed to get the house up to 50 pascals. And then once we start getting close to 50, I'm going to hit time averaging 3 times to get it to long-term average. And then after that long-term average stabilizes pretty well, I'm going to hit the hold button. So we're stabilized pretty well now, and so we can see we got pretty close to 50, 49.8. And because we're in the CFM at 50 mode, it's going to adjust our flow for what it would be if we hit exactly 50, and we can see we're at 43.64. But remember, our actual CFM 50 number is 4,000, so we weren't very close to that because we haven't adjusted for density. In density, temperature difference between inside and outside affects density, and also the elevation at which we're doing our test. So I'm going to clear that hold and then clear the cruise. And the next step, we're going to use the ResNet calculator, 1-point test calculator, to do a test that will take into consideration our accuracy, determine the wind effect on our accuracy, and also correct for density. And we've got a couple of options to get to that calculator. We can go up to Options, Display ResNet Test Calculator, and then that will appear. Or we've got buttons on the side here where we can close that and open it. So this is following the ResNet standard for a 1-point test, and the way in that 1-point test that you determine the accuracy of the test is you take 5 10-second baseline readings and determine the range, the distance between the highest and lowest of those 5 readings. So you write down 5 readings, you look at the highest and the lowest and determine the distance between those two, the span between those two, or the range. And if that range is less than 5 pascals, the difference between the highest and lowest number is less than 5 pascals, then it's considered a standard level of accuracy. If it's between 5 and 10, it's a reduced level of accuracy. And if you're doing a test to meet a code or to meet a standard or do a rating, then you need to add 10% to that number. 10% to your blow dart number to make sure you're within the actual accuracy, accuracy ratings. And statistically, you're within the expected accuracy, and then it'll do a density correction based on the environmental information that we already entered in. We already entered in the indoor and outdoor temperature and the elevation, and it'll do the density correction based on that. So let's do those ratings. Our fan is capped. We can start our baseline, and then start, and we'll let it count up to 10. Once it counts up to 10, we'll enter that first number in. And remember, you need to include the sign. Once it gets to 10, I'm going to hit Start Fan again to get that baseline started again to keep things moving. So negative 3.2 was our first number. Now we're at 10 again, negative 2.8, negative 2.8, and then after we count to 10, each time I'm hitting start again, and it'll start over. Negative 4.2, negative 2.9, negative 2.7. Okay, and then after we've entered those 5, it will display our average baseline reading, and it's going to use this average baseline reading for our baseline, so we don't have to do our baseline again. And then our baseline range is 1.5. We've got a fairly calm wind, so our baseline range is less than 5 pascals, so it's showing that we have a standard level of accuracy. If our range was outside of 10 pascals, then we wouldn't be able to do the single point test, and we'd have to follow either the ResNet repeated single point test or multi-point test, or we could follow some other standard for a multi-point test to determine our accuracy. So now we've determined our accuracy, and we're going to do our blow dart number. Because we're not using the baseline function, and because the calculator will adjust our flow for 50 pascals, that's built into the software, we're just going to use the pressure flow mode. So we're going to change our mode from pressure flow at 50 to pressure flow. And then we'll open our fan, go back, click our back arrow here, and click Open Fan. So we're ready to do our blower air test, and then we'll push the arrow to bring it back. So now we're ready to do our blower air test. I'm just going to play with this a little bit. I'm actually going to bring us, because we're at our baseline was at negative 3.2. I'm going to bring it up to about 53. We could just bring it up to 50, and it will do an adjustment based on whatever pressure we bring it to. It'll adjust it for 50, but I'm going to actually do an induced pressure of about 50. So I'm going to bring it up to negative 53, and I'll just do that manually. So we've got our fan open, and we're just going to start our fan up, and we're going to bring it up to about close to 53. Now once we get it to 53, about 53, we need to do a 10-second time average, because we use 10-second for our baseline, so we need to do 10-second for our other reading. Now if we had greater than a 5 pascal difference between our highest and lowest baseline reading, we could do a longer time averaging period, and that longer time averaging period would tighten that range up, difference between the highest and lowest number a bit. So maybe we could go up to 30 seconds, or maybe we could do a 1 minute average. And if we do 5 1-minute baseline readings, then we would need to do a 1 minute time average for our blower door number too. So that gives us a more accurate test if we have longer time averaging periods for our baseline and longer time averaging periods for our CFM at 50. Okay, so now we'll enter these numbers in. So it's asking for nominal building pressure, nominal fan flow, and that's referring to what's being displayed on the gauge. So that's the actual numbers being displayed on the gauge is what we want to enter in here. So we're at negative 52.7. And again, it's important to enter our sign in there, because our baseline included a sign also. So we need to enter negative 52.7 just like it's being displayed on the gauge, and then 43.47 is our flow when we induced a pressure of 50. And now it'll do an adjusted CFM calculation. So we're at 4021 CFM at 50 is what our actual reading is. So we're much closer to our actual 4,000 CFM reading. And if you do this with a slight wind, it's not the simulator isn't perfect on how it simulates wind, but it does give you a sense of what is actually happening, and giving you some realistic numbers that you can see, that you can visually see. Usually when you run this test, you'll be somewhere, between within probably 30 CFM of CFM at 50. I've run it where it's been within 1 CFM when using a slight wind. So it's random based on the wind condition variability that's in the software, and but it gives you that sense that you're getting a much closer CFM at 50 number when you do that density correction. 4021 is certainly more accurate than 4347. And if you're doing a test for building code, for example, or to meet a certain standard, you need to have an idea of what the repeatability of your test is, the precision of your test, and also how accurate is the test. You can do a very repeatable test and continually get the wrong number. If you want an accurate number, you need to make that adjustment.